Ladies and gentlemen, welcome to this seminar on the Flash DSC-1. Mettler Toledo has been at the forefront of the development of innovative thermal analysis instrumentation and sensors for almost 50 years. The latest addition to our range of high-performance instruments is the Flash DSC-1. This ultra-fast scanning instrument opens up entirely new application possibilities. It allows measurements to be performed that were previously impossible and, as a result, reveals hidden properties of materials. This first slide presents an overview of the topics I want to cover in this seminar. I will begin with a short introduction on conventional DSC and then describe the new Flash DSC-1 and its core component, the ultra-fast multi-star UFS-1 sensor. The results of measurements obtained using conventional DSC instruments frequently depend on the heating or cooling rates used. This is particularly the case with modern, often metastable materials. I want to discuss the influence of scanning rates in detail so that I can point out possible areas of application of the Flash DSC-1. I will then round off my presentation with a number of interesting applications. The slide illustrates the most important aspects of the conventional DSC technique. The sensor has two separate measurement positions. One is for the sample and the other for the reference. The sensor is located in a furnace whose temperature is precisely controlled. The measurement system is several centimeters in diameter. Samples typically weigh 1 to 20 milligrams and are enclosed in a small crucible. The reference sample is usually an empty crucible. A DSC instrument of this type measures the heat that flows in or out of the sample when it is heated. Heating rates are typically between 0.1 and 100 degrees per minute. Measurements can, of course, be performed at controlled cooling rates or under isothermal conditions. This slide shows a typical DSC measurement curve. It was obtained by heating a sample of amorphous polyethylene terephthalate, or PET as it is called, at 10 degrees per minute. The initial startup deflection lasts about 30 seconds. After this, stationary conditions are reached and the measured heat flow is determined by the heat capacity of the sample. Various thermal events occur as the sample temperature increases. First, we see the glass transition accompanied by an enthalpy relaxation peak at about 80 degrees Celsius. This is followed by an exothermic, so-called cold crystallization peak with a maximum at about 150 degrees. In this process, part of the amorphous PET crystallizes from the strongly supercooled melt. Finally, the PET crystals melt and produce an endothermic melting peak in the range of 220 to 270 degrees. Between the glass transition and melting, very small crystallites first form as the sample is heated. With increasing temperature, these crystallites gradually change to more stable crystals. Unfortunately, we see nothing of this reorganization process in the DSC curve because the exothermic and endothermic processes occur simultaneously. In fact, many materials, especially polymers, exhibit thermal events that depend on the DSC measurement conditions. This is because the materials undergo different reorganization processes. I will now explain this in more detail. The slide shows two DSC curves of exactly the same material. The blue curve, measured at 10 degrees per minute, shows the glass transition, cold crystallization, and melting that we discussed in the previous slide. Cold crystallization and melting are reorganization processes that occur during heating. The red curve was measured at 60,000 degrees per minute and looks very different. It shows that a complete measurement result is only obtained when the material is measured at this much higher heating rate. At this heating rate, only the glass transition is observed. Reorganization cannot occur at this extremely high heating rate because not enough time is available. The material is measured in the state it was in before the measurement, or as found. There is no time for any structural changes to occur. We can now draw two important conclusions from this result. Firstly, if you want to investigate the behavior of materials in technical processes, such as crystallization processes in injection molding, the heating rates used for the measurement must be comparable to those that occur in the actual process. Secondly, to perform such measurements, we need a DSC instrument that can measure at a very wide range of heating and cooling rates, in particular at high rates of about 100 to 1000 degrees per second. Here, conventional DSC instruments have a performance limitation because their maximum heating rates are only about several hundred degrees per minute. In other words, they are about 100 times too slow. They do, however, have the advantage that larger samples can be measured in crucibles. The aforementioned considerations led Mettler Toledo to develop a new type of rapid scanning DSC instrument using the very latest technology. The instrument is called the Flash DSC-1 and is shown in the slide. The Flash DSC-1 combines a DSC chip sensor based on MEMS technology, an innovative, patented measurement and control concept, and a functional ergonomic design. In its development, great importance was placed on simple sample preparation and ultra-high heating and cooling rates. The scanning rates should, however, overlap those of a conventional DSC instrument. The overlap range is shown in the inserted diagram. The Flash DSC-1 provides heating rates of up to 40,000 degrees per second, that is 2,400,000 degrees per minute, and cooling rates of up to 4,000 degrees per second, or 240,000 degrees per minute. This means that the Flash DSC-1 allows measurements to be performed over a scanning rate range of 4 to 5 decades. The Flash DSC-1 and the DSC-1 together cover a scanning range of more than 7 decades. The temperature range of the Flash DSC-1 is from minus 95 degrees Celsius to plus 450 degrees Celsius. Cooling is provided by an optional intracooler. In order to achieve the ultra-high heating rates, the mass of a sample is typically a few micrograms down to nanograms. The preparation and insertion of such a very small sample is performed sitting comfortably in front of the instrument. To ensure optimum thermal contact, the sample is positioned directly on the sensor. This is done using a microscope. This ensures simple and reliable sample handling. As you can see in the picture on the left, the sensor can be quickly and easily changed in less than a minute, thanks to the innovative sensor support. Used sensors with their adhering samples can be safely stored in a chip sensor box. This allows measurements to be repeated later on with the same samples. I now want to describe this new sensor in the next 2 slides. Here we see a schematic diagram of the new chip sensor. This is the heart of the Flash DSC-1. The Flash DSC-1 uses the multi-star UFS-1 sensor. UFS stands for ultra-fast sensor. This sensor is a chip sensor based on MEMS technology. The heaters and temperature sensors are incorporated on a small, extremely thin membrane that is only 2 micrometers thick. The construction is in fact a complete miniaturized DSC furnace for sample and reference. The picture on the left shows the UFS-1 sensor. The membrane with the actual sensor is mounted in a ceramic frame together with the electrical connections. The picture in the middle is an expanded view of the actual sensor. It consists of two membranes with identical furnaces. Each sensor is in fact a complete DSC cell. In the picture, the sample is placed on the upper part of the sensor. The lower part is the reference, which usually remains empty. The high degree of symmetry of the differential sensor results in flat and extremely reproducible baselines. Even at the highest scanning rates, the measurement curves exhibit a degree of reproducibility never before achieved in a DSC instrument. The picture on the right is an enlarged view of the sample side of the sensor containing a sample. To achieve a homogeneous temperature profile and to simplify sample preparation, the active part of the membrane area with a diameter of 0.5 millimeters is coated with aluminum. The 8 thermocouples and 4 resistance heaters are also visible. It is always advisable to use a wide variation of heating and cooling rates when kinetic processes significantly affect the formation of structure in the material under investigation. In such cases, the structures depend on the cooling conditions and are often metastable. The structures can change as a result of a temperature change or during isothermal storage. Polymers are examples of materials that form metastable structures. Due to their molecular structure, they produce only small crystallites on cooling from the melt. The size of the crystallites depends on the crystallization temperature and hence on the cooling rate. Reorganization can occur on heating. This means that the crystallites melt and at the same time recrystallize to form more stable structures. The DSC melting curve therefore shows the result of the reorganization and not the melting of the original crystallites. The degree of reorganization depends on the heating rate. Metastable structures are formed in many other materials besides polymers, for example, polymorphic substances. The different phases and their distribution depend on the crystallization conditions. In blends and alloys, diffusion processes, phase separation, mixing and demixing, as well as other time-dependent processes lead to the formation of metastable structures. In addition, many composites form structures that depend on the cooling conditions. This is often due to processes that occur at the inner surfaces which form at the phase boundaries. The schematic diagram shows a typical Flash DSC temperature program. In the first heating segment, the sample is usually melted in order to optimize thermal contact with the sensor. In the second, controlled cooling segment, defined structure can be produced. In the third, heating segment, the sample is measured until it finally melts. Both the cooling and the heating segments are measured and can be repeated more than 100 times in a measurement program using different scanning rates. This allows the cooling rate dependence of a crystallization process to be measured in a very short time in a single measurement program. Reorganization processes can be investigated by varying the heating rate, or even completely suppressed by choosing suitable heating rates. If reorganization occurs, the structure of a material changes during heating. Examples of reorganization processes are phase separation with mixtures or the separation of certain phases in alloys. In the case of polymers, small unstable crystallites first melt and then recrystallize on further heating to form more stable crystallites. The transitions of different metastable polymorphic phases are also reorganization processes that depend on the heating rate. The measurement curves in the inserted diagram show the reorganization of isotactic polypropylene on heating as an example. Before each measurement, the sample was cooled at 1 degree per second from the melt. The heating runs were then performed at heating rates between 10 and 2000 degrees per second. If no reorganization occurs, one expects the maximum of the melting peak to shift to higher temperatures at higher heating rates. This is the case at heating rates above 200 degrees per second. At lower heating rates, one observes the opposite behavior. The lower the heating rate, the higher the melting temperature. In this case, the time available during heating is long enough for more stable crystals to form that do not melt until higher temperatures. The lower the heating rate, the higher the melting temperature becomes and the less information the melting peak contains about the original sample. The kinetics of structure formation can be studied by performing cooling measurements at different cooling rates. An important advantage of the Flash DSC-1 is that the cooling rates correspond to those of technical processes, such as those that occur in injection molding. This allows you to follow the formation of structure that occurs in the process. In addition, you obtain information about the function and action of additives, for example of nucleating agents, under near-process conditions. The data obtained from cooling experiments can be used to improve calculations based on models. It is often advantageous to use isothermal experiments to investigate the kinetics of processes involving structure formation. The sample is first cooled so rapidly from the melt to the crystallization temperature that no crystallization occurs. Following this, the heat flow is measured continuously during the isothermal crystallization process. Very fast chemical reactions can be investigated in much the same way. Besides the need for high cooling rates, the transition region between the cooling and isothermal segment should be as short as possible. The diagram shows the curve of sample temperature in the transition region from a cooling segment at 1000 degrees per second to an isothermal segment at 50 degrees Celsius. In this example, the transition region of the Flash DSC-1 lasts 5.5 milliseconds. The maximum overshoot is 0.02 degrees. This slide summarizes the most important application areas of the Flash DSC-1. These include the analysis of processes involving complex and rapid formation of structure, as well as the determination of the reaction kinetics of fast reactions. The investigation and comparison of the action of additives at cooling rates directly relevant to the process. Because the scanning rates are so high, comprehensive thermal analyses of materials can be performed in a very short time. For example, the investigation of the cooling rate dependence of a crystallization process in a range of more than 3 decades takes less than 30 minutes. The Flash DSC-1 allows the investigation of very small amounts of sample down to just a few nanograms. Data can be measured under actual process conditions. This can be used in simulation calculations, for example, to optimize the performance of tools. Just as in conventional DSC, the melting point transitions of pure substances can be used to check temperature accuracy. The slide displays the corresponding curves at the melting points. The heating rate was 100 degrees per second. Besides the melting peaks of the metals gallium, indium, and tin, the solid-solid transition of adamantine at minus 65 degrees Celsius is also shown. This transition is suitable for checking the temperature accuracy below room temperature. Also shown are naphthalene and HP53. Both substances can easily be removed from the sensor. The need for heating and cooling rates higher than those available with a conventional DSC is driven by potential applications. I would now like to discuss some typical applications. The diagram shows melting curves of polyethylene terephthalate, or PET as it is commonly called. The material was allowed to crystallize at 170 degrees Celsius for 5 minutes before each measurement. The measurements were performed at heating rates between 50 and 1000 degrees per second. The diagram displays several measurement curves that exhibit a double peak in the melting region. At higher heating rates, the low temperature peak is shifted to higher temperatures and the high temperature peak to lower temperatures. This diagram summarizes the results. The peak temperatures are displayed as a function of the heating rate on a logarithmic scale. The blue points represent the low temperature peaks and the red points the high temperature peaks. The blue curve is typical for melting processes without reorganization. Crystallites melt that were formed during crystallization. The behavior of the high temperature peak is characteristic for the melting of crystallites that were formed through reorganization on heating. The lower the heating rate, the more time the crystallites have to become perfect, and hence the higher their melting point. At a heating rate of 1000 degrees per second, only one peak is measured. Reorganization is suppressed at these high heating rates. The diagram also shows the extent to which the heating rates of the conventional DSC-1 of about 0.1 to 200 degrees per minute and the Flash DSC-1 from about 10 degrees per minute onward overlap. This next example also shows the effect of reorganization on heating. Isotactic polypropylene was cooled very rapidly from the melt at 4000 degrees per second to obtain an amorphous sample. The sample was then heated at heating rates between 5 and 30,000 degrees per second. To facilitate comparison, the curves are displayed in heat capacity units and are also normalized with respect to sample mass and heating rate. In this heat capacity presentation, exothermic processes are shown in a downward direction. The glass transition appears at about 0 degrees Celsius, followed by the exothermic peak due to cold crystallization. The melting peak is between 130 and 150 degrees. The curves show that with increasing heating rate, the crystallization peak shifts to higher temperatures and the melting peak to lower temperatures. At heating rates above 2000 degrees per second, the areas of the crystallization and melting peaks start to become smaller. At about 30,000 degrees per second, crystallization no longer occurs. Even on heating, the material remains amorphous and exhibits only a glass transition. The slide displays cooling curves obtained from measurements performed on isotactic polypropylene at cooling rates between 10 and 500 degrees per second. The curves show how the crystallization peak shifts with the cooling rate. This diagram summarizes all the measured peak temperatures as a function of cooling rate. The measurements were performed at cooling rates between 0.1 and 1000 degrees per second. Several measurements were also performed at cooling rates between 0.02 and 0.8 degrees per second using the conventional DSC-1. The results are shown as red points. The black points are the measurements obtained using the Flash DSC-1. The results from the two techniques show very good agreement in the range of overlap between 0.2 and 0.8 degrees per second. The measurement curves recorded at cooling rates above 50 degrees per second show the presence of a second crystallization peak at about 30 degrees Celsius. Other metastable structures are apparently formed at these low temperatures. The corresponding peak maximum temperatures are shown blue. Fast isothermal processes can also be measured with the Flash DSC-1. The slide shows some of the measurement curves obtained from the isothermal crystallization of isotactic polypropylene at crystallization temperatures between -10 and +110 degrees Celsius. The curves between 46 and 100 degrees illustrate how the peak maximum changes as a function of the isothermal crystallization temperature. This diagram summarizes all the measurement results. The reciprocal peak time at the peak maximum of the measurement curve is displayed as a function of the crystallization temperature. The reciprocal peak time is a measure of the crystallization rate. Two different crystallization processes are apparent. The heterogeneous crystallization below 40 degrees is faster than the crystallization at higher temperatures. In this application, differences in nucleation were investigated by varying the cooling rate. Samples of polyamide 11 with and without filler were cooled in a conventional DSC at 10 degrees per minute and in the Flash DSC-1 at 1200 degrees per minute. The red curves are of a pure polyamide without filler. The black curves were measurements of a polyamide that contained 5% nanofiller. In the conventional DSC-1, the unfilled polyamide crystallizes at higher temperatures than the filled polyamide at the low cooling rates used. The opposite effect is observed at the high cooling rates of the Flash DSC-1. The filler then functions as a nucleating agent. The temperature at which kinetic processes take place can be shifted at higher heating rates. An example is the overlap of melting and decomposition, which occurs in many organic materials. Saccharin is shown here as an example. At lower heating rates, decomposition begins before the melting peak. At higher heating rates, decomposition is shifted to higher temperatures. The morphology of substances with different polymorphic phases depends on the thermal history, such as the cooling and heating conditions. The slide shows the complex melting behavior of phenobarbital. The original material has a melting peak at about 180 degrees Celsius. After cooling at 100 degrees per second, it is amorphous. If this sample is seeded with small needle-like crystals, different phases are formed on heating depending on the heating rate used. 6 different polymorphic phases can be recognized in the measurement curves. The application examples show that the Flash DSC-1 is the ideal complement to conventional DSC. The instrument provides an extremely wide range of heating and cooling rates. This is a very important factor for the characterization of modern materials. The data obtained allows for the optimization of production processes. The technique is particularly interesting because materials can be measured at the cooling rates at which they were produced. The fast and variable measurements allow materials to be characterized in a very short period of time. Materials or production conditions can be improved through measurement of structure formation at cooling rates relevant to those that occur in production. This slide summarizes the advantages of the Flash DSC-1. The ultra-high cooling rates of the Flash DSC-1 enable processes involving structure formation on cooling to be measured. The ultra-high heating rates reduce measurement times and can be used to investigate reorganization processes or to prevent reorganization from occurring. Measurements can also be performed at relatively low heating rates thanks to the high sensitivity of the Flash DSC-1. Due to this, the heating and cooling rates overlap to a certain extent with those of conventional DSC. This allows for direct comparison of experimental results. The temperature range of the Flash DSC-1 with the multi-star UFS-1 sensor is -95 to +450 degrees Celsius. The application-oriented ergonomics and functionality enable easy and rapid sample preparation. If you want to learn more about the Flash DSC-1 or other Mettler Toledo thermal analysis products, please visit our website or call your local Mettler Toledo sales specialist. You can also obtain information about our handbooks, brochures, webinars, and other products. This concludes our short visit to the exciting new world of ultra-fast DSC measurements. Thank you for your attention.